Welcome back, science students, to today's explainer. I am absolutely pumped to have you all here because we are about to unpack a topic of truly cosmic proportions. We spend so much time studying the materials we can actually touch, pour, and breathe right here on Earth, but today, we're zooming way, way out. We are going to unlock the secrets of a state of matter that is literally the fundamental building block of the universe itself. To kick things off, let me pose a quick question to you all. What do you think is the absolute most common state of matter in the visible universe? I'll give you a little hint. If you're guessing a solid, a liquid, or a gas, you need to think much, much bigger. That's right. Over 99% of all ordinary, visible matter in the entire universe exists in a state you almost never encounter in your daily life on Earth. It's called plasma. Just take a second to wrap your head around that number. More than 99%. It absolutely blows my mind every single time I think about it. But before we dive into the deep physics of how this actually works, let's map out exactly what we're going to cover today. Here is our syllabus for today's explainer. First, the universe's dominant matter. Then, defining the fourth state. Third, a spark of history. Fourth, generating laboratory plasma. Fifth, complex plasma phenomena. And lastly, everyday and future applications. All right, let's jump right into Section 1, the universe's dominant matter, from stars to solar winds. Look around. Here on Earth, naturally occurring plasma is incredibly rare. I mean, sure, you might see it in a random lightning strike or, if you're lucky, the aurora borealis. But out in the cosmos, it is literally everywhere. Those massive astrophysical phenomena, like the burning core of our sun, the solar winds whipping through our solar system, or those crazy accretion disks spinning around black holes, all of that is plasma. We are essentially living on a tiny, cool, solid liquid gas rock floating in an infinite ocean of plasma. Moving right along to Section 2, defining the fourth state, the physics of plasma. So plasma is often called the fourth state of matter, coming right after solid, liquid, and gas. It happens when a gas gets subjected to extreme heat or incredibly strong electromagnetic fields. This causes it to undergo what we call an appreciable degree of ionization. Now, what does that mean? It means the electrons are literally stripped away from their atoms, leaving behind this wild soup of unbound positive ions and negative electrons. And because it's packed full of these electrically charged particles, plasma behaves in ways a normal gas simply cannot. There is a very hard line between a standard gas and a plasma. In a standard gas, particles only really interact when they physically bump into each other. We call those short-range binary interactions. Plus, regular gases are excellent electrical insulators. But plasma, because of those charged particles we just talked about, it's ruled by long-range collective motion. The particles are highly electrically conductive, and they respond instantly to electromagnetic fields, moving all together in this beautiful, complex, synchronized dance. Which brings us to Section 3, a spark of history, how we discovered plasma. Before we could study it way out in the stars, we had to actually discover it in the lab. Our understanding comes directly from the early history of electricity research. Way back in 1803, Vosley Petrov and Humphrey Davy independently discovered the electric arc. Fast forward to 1831, and Michael Faraday was systematically investigating glow discharges. Then, in 1879, Sir William Crookes realized this stuff was behaving unlike any known substance and boldly proposed a fourth state of matter. But, you know what? It wasn't until 1928 that it finally got its official name. And that name came from the brilliant chemist and physicist Irving Langmuir. In a 1928 paper, he officially coined the term plasma to describe this region containing balanced charges of ions and electrons. Now, what is truly fascinating here is exactly why he chose that specific word. According to his colleagues, Langmuir noticed that the way thermant ionic electrons were transported through this ionized gas reminded him exactly of the way human blood plasma carries red and white corpuscles along with germs. He literally used a biological analogy to name a fundamental principle of physics. How cool is that? Let's dive into Section 4, generating laboratory plasma, creating the cosmos on Earth. Okay, so this is the actual recipe for creating the cosmos right here in an industrial laboratory environment. First, you introduce a neutral dielectric gas. That's really just a fancy way of saying an electrically insulating gas. Second, you apply a massively strong electric current across it. Third, you crank that voltage until it stresses the gas past its breaking point. This triggers what physicists call a Townsend avalanche. Basically, an electron smashes into an atom, knocking off more electrons, which then impact more atoms. It creates this rapid, cascading avalanche of millions of ions and electrons. And boom, just like that, you have achieved an ionized plasma.
Next up is Section 5, Complex Plasma Phenomena, Bizarre Behaviors.
Because plasma is such a complex system, it spontaneously forms the most bizarre, totally unexpected structures. Take filamentation, for example. This is where plasma forms these self-focusing string-like structures. You can actually see this naturally in lightning or the auroras, and when it interacts with magnetic fields, it literally forms magnetic ropes. Then you have impermeable plasma. This is just wild. It's a thermal plasma that actually acts like a solid, impermeable wall. Cold gas literally bounces right off it. Scientists have even used this invisible plasma wall to synthesize complex nanomaterials.
Finally, Section 6. Everyday and future applications, harnessing the power.
You might not even realize it, but we use atmospheric and low-pressure plasma discharges constantly to manufacture the modern world around us. We use thermal plasma arcs for heavy-duty metal welding and cutting. We use it for surface coating and spraying materials. Hey, if you have a smartphone or a computer, the microelectronics inside were etched using capacitively coupled plasma. We even use glow-discharge plasmas inside everyday fluorescent lighting. And then there's that last point on the list, which might just be the most exciting frontier of all: plasma medicine. To achieve some of these amazing breakthroughs in plasma medicine, researchers have developed what is known as a dielectric barrier discharge. This tech allows us to generate a non-thermal, low-temperature atmospheric plasma. Way back in the mid-1990s, scientists proved that this cold plasma is incredibly effective at inactivating harmful bacterial cells, all without burning the surrounding tissue. This has completely revolutionized biological and healthcare research. It proves that this cosmic fourth state of matter can literally be used to heal us. And well, that brings us to the end of our explainer today. We've journeyed all the way from the vast, plasma-filled expanse of the intergalactic medium down to a tiny spark in a laboratory, and finally out to the absolute cutting edge of medical science. So I want to leave you, the next generation of science students, with this final thought. As we continue to master the fundamental building block of the universe, what revolutionary technologies are you going to unlock next using this fourth state of matter? The universe is waiting for your answer. Keep studying, keep questioning, and I will see you in the next explainer.